Hey everybody, I thought I'd make another little eyepiece video, and this one here is mainly about terminology and kind of helps you choose whether or not one eyepiece is better for you or not, as far as what focal length and apparent field of view, whether you should get a Plossl or a super wide angle, things like that. I'm using this telescopius.com website. It's got a real nice simulator on it. It's a free website. If you want, you can create a username and you can save all your information in there as far as what telescopes you have, cameras, eyepieces, things like that, and it kind of makes it easy to get a quick reference. Now, in this case, right now, we've got the Andromeda galaxy showing up here, M31, and it's one of the first things that it says down here at the bottom. This tool was designed to check framing and not visual magnitude, and it says that objects will look dimmer in your eyepiece. So this is more like what you might see after you process a picture. It's much dimmer in the eyepiece. The bright area would be kind of a faint fuzzy blob, and in a larger telescope you'd start to pick up some of this other detail out here, especially if you're in a nice dark area. Anyway, we'll say that we're starting with a 6-inch f5 telescope. So like I say, if you have a 6-inch Newtonian, it's usually about this. So it's got your focal length at 750 millimeters. That's pretty common. The aperture, 6 inches, is equal to 150 millimeters. If you divide 750 by 150, you'll get f5. Shows here we don't have any kind of Barlow, so it just says 1. For an eyepiece, it's showing a pretty common eyepiece, 25 millimeter. It says 52 degree apparent field of view, which is basically just a Plossl. A super wide angle would be more like 70 or in the mid 60s. But one thing you notice, the magnification is going to be the same regardless of whether you get a Plossl or a super wide angle, or, you know, an old Kellner type. If you get some of these older eyepieces, which a lot of those are just narrower as far as the field. But what this is doing here, it's showing me this window of approximately how much area of sky I would see. So you can see the brighter part of M31 would show up in your telescope, and to see this fainter stuff in an eyepiece, you need to be in a good dark location and really have a pretty large telescope too. So now I just turned on this button here, compare with other field of views, because that's one of the things I wanted to talk about. So that one I bought that was called Angel Eyes was supposed to have a 70 degree field of view. And they have a set of lines here for 72. So what this is telling you is that if you buy a 25 millimeter eyepiece that has 70 for a apparent field of view, it'll give you a much wider field, but it's still the same power at 30 power. Now you can also buy considerably wider apparent fields of view and get out your wallet. Those are the ones that get real expensive. That one I bought, that Angel Eyes, it's a generic brand name. I've never even heard of it. I saw it on eBay and it was like $45, and I thought, I'm just going to get it. I took a chance, and I like it pretty well. But one of the things I'd been wondering about was how much different is it than other eyepieces. Let's see, so that one's 27. It's right there, so we'll get that the same. So it's saying that with the 6-inch Newtonian, see, it's almost 28 power, so it's not much of a difference between a 27 and a 25. So really, the only reason to, if you already own a 25, the only reason to consider buying a 27 was if you just wanted more field of view, because maybe they just don't offer a 25 with that. So it gives quite a bit more. Now, I also have a 32 millimeter Plossl, which should give a considerably wider field of view than that 25, but it's smaller here. And I had mentioned in my other video that it didn't do very good in my 180 millimeter Maxitov. It's a 7-inch Mac F15. It's got like 27 100 millimeter focal length, so it's really high power. Let's see, this here says that with the 32 millimeter Plossl, my real field of view would be 2.21, so 2.2 with that at 23 power. Now, the 27 should be, it's even a wider field of view, but it also gives me something larger to look at, which is the whole idea of this super wide angle. You get that. We'll change this to 70. And you go from 2.2 to 2.5. So there's not a huge difference, but it's bigger. And in my case, it ended up being better because the 32 didn't look that good. So it's something, to think about. It's not, it's easy to buy another eyepiece and find out it's not a lot different than what you had. Another thing to consider is how much power is too much power. So we'll get up a little calculator here on that, because especially if you buy an inexpensive telescope, they like to advertise that it's got all kinds of power. And if you get talking to people that have been doing this a long time, you find out you can get high power out of basically any telescope if you put the right eyepiece on it, and maybe even have to use a Barlow. But if you go overboard, it'll deteriorate the image a lot. It gets really dim and harder to focus. So sometimes it ends up just, you're better off to have a better quality view, just because it's more comfortable that way, and you're more likely to spend more time looking through your telescope. So we'll go over a little calculator here. Now, one thing I had always heard a long time ago was that the maximum magnification for a telescope was between 50 and 60 power per inch of diameter. So if, let's say, you've got a 4-inch diameter telescope, and you go with your 50 power times 4, obviously gives you 200. So that would tell you 200 is your maximum magnification. Now, say if you use the right setup of eyepieces, you can get more, but it doesn't mean it's going to be a good quality view. Matter of fact, it won't be likely. And my experience has always been, if I tried to max out the power here, it's not as good as if I was looking at 50 power or 100 power or 120. So what I've learned over the years is, when you do try to get maximum high power, you want it to be a real clear, steady night. It doesn't necessarily have to be super dark. You could be in the city, you could have a bright moon, but you want the weather to be steady. If there's a front coming through, if it's windy, something like that, it's a lot harder to get a nice view at high power. It'll just magnify all the distortion and junk. And also, the higher the object is in the sky, the easier it is to use high power. If you notice, like, say when the sun's coming up or setting, it's changing color, and it also appears to change size. Especially, a lot of people notice that with the full moon. If you see a full moon coming up, and it looks a lot bigger when it's down low to the horizon than when it gets up higher. And that's just because you're looking through all that atmosphere. It just kind of distorts it some. So you end up, that's fine for viewing, but it's not so good for high power. It's better if it's up high somewhat. Now let's think for a minute about my Maxitov telescope at 180 millimeter f/15. It's specifically designed for high power. So 180 millimeters, it's a 7 inches approximately. So times 50 is obviously 350. If you go times 60, it could be 420. So between, say, 350 to 420 power is the maximum usable power, is what's supposed to be. And when I put in a, say, 25 millimeter eyepiece, which is pretty wide, I'm getting like 108 power out of it. And when I bought that 27, that angel eyes thing, it just goes down to 100 power, and it looks almost the same. And the 32 millimeter that I had tried to use, which I didn't really like, was 84 power. So that kind of telescope, it's always looking at a pretty small piece of sky, and it can be kind of challenging to find your objects when you first start getting it set up. Once I have everything lined up, it's not too difficult to find things, but sometimes when I'm trying to calibrate the first set of stuff, it's pretty difficult. Okay, and then what about if you're wanting to go with the minimum power, the lowest power? Let's go back over here to Telescopius for a minute, and I'm going to make this a little less. Let's say that you want to see all of Andromeda Galaxy, and you say, man, I want to get even lower power, because that's what usually happens when you're looking at these large objects. So let's go, you can actually get a 40, put the number in there, and it won't be, you can get a 40 millimeter eyepiece, and those things, the apparent field of view is supposed to be around 43, 45. And if you notice here, it says, let's see, it's about 19 power, 18.75. And the real field of view says 2.29. Well, that's actually a little less than what my 27 was. That's one of the things I was thinking about when I bought it. The 27 at 70 goes up to 2.5. So it's actually, instead of 19 power, I've got almost 28 power, so it makes it bigger. And it's actually a wider area. And one thing I noticed too when I was thinking about this, you know, you can buy a 2-inch eyepiece instead of your 1 1/4 to get larger views. But you notice this calculator on here does not ask you if you have a 2-inch eyepiece or a 1 1/4, or anything else. And what it amounts to is, if you buy a 2-inch eyepiece, you're looking at a larger piece of glass, so it just gives you a larger picture. It's just kind of like if you had a large screen on your computer versus a small screen. And also, the 2-inch eyepiece, since it has a larger barrel, they can give you a higher focal length number, because this is another one of the issues. They get away with doing that, the 40 millimeter, because apparently what I've been reading is a 1.25 inch eyepiece, if you take it to millimeters, is about 30 millimeters. It's like 30.6, I think. We can double check that real quick. So 1.25 inches times 25.4 millimeters per inch. Okay, 31.75. According to that, you should be able to almost get to 32 millimeter. What I've read is that what really matters is what they call the field stop. And that, I'm trying to figure that out. And what that amounts to is the maximum field stop diameter you can have in an eyepiece is the diameter of the barrel. And I think the diameter of the barrel is actually the outside diameter when they figure 1 1/4, so the inside slightly less. So if you start getting wider than that, you start to see the inside of the barrel when you look down the eyepiece, and you'll get weird vignetting and stuff. But with a 2-inch, then you're getting almost 51 millimeters. So you can get a higher focal length and lower magnification, which will give you a wider view. So if you go to a 2-inch eyepiece, you'll get an actually wider view as long as you use less power. So let's go to like a 40, I guess, millimeter. That's, now see, it says if you have that with the 70 apparent field of view, you've got 3.7 degrees apparent field of view, and it gives you a pretty wide view. As a matter of fact, I've got a 55 millimeter 2-inch, but it's a Plossl. And if I put it in my 6-inch, I thought it looked fairly good. But see, it's pretty low power. And that might act, that's one of the things I was going to get at. I read a while back that you can go like maybe 4 power per inch of diameter minimum. So a 6-inch, it's saying the minimum power would be around 24 power. And so saying going down to almost 14 power might give you a less quality image. So I've used an eyepiece, and I wrote the number in there wrong. Let's see, I wanted 52. Okay, so it's 3.8, which still looks pretty wide, but still shows the same magnification. And I've done that, and like I say, I thought it looked pretty good. And I originally bought that eyepiece with a old Celestron C8, and it looked really good in that to go down from a 2,000 millimeter focal length. But I also, a while later, I picked up a 35 millimeter Plossl because I read that would give me larger view. So see, when I do that, I go up to 22 power almost, and that's closer to what the manufacturer would say for the minimum magnification. So it made it larger, so it'll also be a little, like I said, it might not be brighter, but it'll be larger, and that'll help out. And it actually could be a little brighter because it's within the usable range. And that's one thing to think about when you go to real high power. The image always keeps getting dimmer because you're grabbing light from a smaller piece of the sky. So that's really one of the reasons why you have maximum usable power too. It's kind of like, if you think about it, if you take a light bulb and you don't have a shade on it, it's a lot brighter. And if you were to cover it up and put a hole in the cover, the smaller the hole, the less light that gets out. So it's kind of like the same idea here. You're just looking at it may sound a little weird, but when you go to higher magnification, since you're looking at such a small area, there's just less light there to grab, even if the object there is the same. And it really does hold true. You really notice it when you get to real high magnification. Sometimes when you go to a high power eyepiece, it's pretty hard to find your object and see it. The one thing that's neat here too, let's say you're thinking about buying another eyepiece, and let's say all you have is a 25. And let's say you go over here and find M13, which this isn't the best picture of it in the world, but it gives you an idea where it's at, and it's actually a little bigger than this, I think. But you can find out how much different it is with a different eyepiece. So let's say, usually if you want to see an appreciable difference, try to double your power if you can. So let's say we'll go down from 25 to we'll just say 12 or 12 and a half. I've got it on 12. And we went from about 30 power to 62. And that's plenty usable in a 6-inch. So 6-inch times 50 power, it says it can go all the way up to 300 power. So then let's say you go up to, let's go to 6. So you get a 6mm eyepiece. Now 125 power. As you can see, it's got a lot bigger, and you can actually start to see all the detail coming out around it. And if you're actually looking at it in here, the center of this isn't going to look like a big bright blob in an eyepiece. It'll be pretty faint and gray, and if things are going good, you'll actually be able to kind of see the stars. There's hundreds of thousands of stars in it. And then that brings up the idea of Barlow lenses. A lot of, especially low-cost telescopes that you see advertised as a kit, they want to advertise how high a power they got. And one of the things they'll do is throw in a cheap Barlow lens so that they can say, look, we've got 450 power out of say a 3-inch telescope or something. And it's like, yeah, it's possible to get it, and you might even like it if you've never looked through a telescope. But if you start looking through different telescopes and different eyepieces, you realize that you can get a lot better quality image if you don't overdo it. So, like, say if you see a telescope and they say it comes with a 20mm eyepiece, a 10mm eyepiece, and a 2-power Barlow, well, when you go from 20 to 10, you're already doubling the power. So it doesn't do you any good to use the Barlow with the 20mm, because that's the same as using the 10mm eyepiece. And the 10mm eyepiece would actually likely give you a better view. You're not having as much extra glass in there. But you can use them. People that are into planetary photography use them a lot, and some people buy really expensive ones. I've actually been surprised what a Barlow lens can do if you've got a pretty long telescope and you're trying to take pictures of Jupiter or Saturn or Mars. because when I would try to get it centered up in there and focus it, the live view is actually pretty terrible. I mean, it's really bad. I was wondering, what am I doing? And but if I stacked several thousand frames and learned how to process and sharpen, surprisingly, you can get something pretty nice. Anyway, I wanted to show you this simulator and kind of just talk a little bit about the idea of what these fields of view, apparent fields of view, are with eyepieces and how it does make a difference. And the field stop part, that's basically, they put that in there. Usually it's smaller than the diameter of the barrel. And they put that in there because if they leave the field of view at the full size of the barrel, the outer edges of it look pretty crappy. So they just go ahead and give you a narrower field of view to give you something good quality. So then that tells you that if somebody makes a really cheap eyepiece and they just want to say, look at our wide field of view, they just leave that field stop out and give you the full diameter of the barrel. And it would be a wider field of view, but it might not be all that great a quality. And like I say, that one eyepiece I bought, that Angel Eyes, it's not an expensive eyepiece. And I'm sure if you compare it to a really expensive one, like a $300 or $400 eyepiece, it's not even going to come close. But let's see, in case I didn't show you how to find this simulator here. Of course, you go to telescopius.com. It's inside this toolbox. You can go to Telescope Simulator, and it brings up this menu. So you can put in your different eyepieces. You can also select cameras for astrophotography. If you've got a DSLR or a planetary camera or something, you can figure out the size of your sensor by, you just look it up, you know, like Google it, what your camera is, and in the specifications, it'll tell you how many pixels there are and the sensor size and that. And this will give you a lot more information. So that makes it easy to, that's nice for planning your photography. Like if you're planning to take a picture of M31 tonight, and I see a lot of people in the Facebook groups asking things like, okay, I've got a 200 to 600 millimeter zoom lens or something, and they're trying to decide how much to zoom in. This thing here will give them a pretty good idea of what your area of sky is. So anyway, hopefully this helps you out some if you're trying to figure this stuff out. Hope you enjoyed the video.